Hi, and welcome to this tutorial for the quantum algorithm for simulating open quantum dynamics. The goal of this tutorial is to first introduce you to the general quantum master equations, the master equation we propose for simulating open quantum dynamics, and also show you some details of the model we choose and how to use quantum computer to simulate open quantum dynamics. So let's begin with some introduction to the GQME, Generalized Quantum Master Equations. Here are the explicit form of this GQME. And the first part, the sigma t, the density matrix is used to describe the system of interest. And this part with the Liouville is for the system of interest itself, while the third term is used to describe the effects of the surrounding acting on the system of interest. And this pink operator in the middle is what we call a memory kernel. And from its name, you know that it can capture the memory of the system, and thus allows the GQME to be applicable for the non-Markovian systems. Moving on. Because it is not straightforward to transform this GQME into a quantum circuit all by itself, so we take a roundabout. And we first calculated the non-unitary time evolution operator, this G of t, or the propagator of the system, with the GQME. And then we can apply this propagator in this form, and we basically simulated this equation on our quantum computers, in which we can basically transform this propagator into quantum circuits, apply on the inertial state, the sigma 0, and then we can obtain the system dynamics by measuring the quantum state in the circuit. And this propagator, G of t, can be obtained with some exact dynamics measures, such as the TT-TFD. Next, let's talk about the quantum algorithms. So for our case, the input state is usually described the initial state of a system. For example, for an FMO complex, which has 7 sites, we usually pick sites number 1 and 6 as our initial state. Then the quantum states are used to encode the G of t, the propagator here. And we can perform those quantum gates and compose them into quantum circuits and run it on the quantum machine provided by IBM, as shown here, or on the 3D CQEDs that are provided by our experiment collaborators. And finally, we'll measure the quantum state on the quantum computer at the end, and then we can obtain the system dynamics in the forms of sigma t, as illustrated by this little animation here. Next, let me introduce you to the QSCID package. To begin with, we already made the tutorial Jupyter Notebook, which describes all the information you need. And actually, these screenshots are taken from the Jupyter Notebook. What I'm doing here is to help you go over the most essential code lines, and hopefully this will facilitate you in reading this Jupyter Notebook. And I will let you know what is each line doing and make it easier for you to run the program by yourself and on your end. Okay, this QSCID package is developed by IBM Quantum, and with all the coding that facilitate you to basically build your own quantum circuits and submitting your job to the IBM cloud, and also do the quantum simulations. And to begin with, we first load in some commonly used Python packages. And these QSCID packages are very handy to use. This unitary gate actually has a lot of built-in gates that basically gives you a lot of options for the quantum gates. And this plot histogram function and later this plot circuit layout function is useful for the visualization part. This operator functions allows you to build some custom operator or some custom quantum gates from the unitary matrix you give. And finally, this transpile function allows you to transpile from a unitary matrix into a quantum circuit. To begin with, I highly recommend you to apply for your own IBMQ account. And you can refer to these two websites to learn how to obtain your account, obtain your personalized token, and load this token into your backend. And thus, it will be easy for you to submit in the job. You can find more details in the Jupyter Notebook tutorial file. Moving on to the quantum circuit preparation. Our specific model are working with a 4x4 G matrix. And we're using 16 different files. In each file, we recorded the time, the real and imaginary part of a specific matrix element. So we need all 16 of them to build the 4x4 matrix. And in each file, we have 4,000 elements. So which means in all, we have 4,000 G matrix. Basically, what this doing is it will take the input from the file and then it will build a big G matrix, which has 4,000 4x4 matrix. Next, we build a quantum circuit. So because the G itself is not unitary, so we undergo the mathematical process called dilation. We have a separate tutorial video for the dilation, and you may refer to that. So here I just go over briefly. This is how you build the unitary U first from the G matrix to input, and then make it unitary. And next part, we basically first choose the number of shots. This is for the number of shots for the quantum simulator or the quantum machine to make a 4,000 shots, and then it will record the average of the results. This row is our input state, and we set it to be 1000. And because after the dilation, U first becomes an 8x8 matrix, so we need to add 4 extra dimensions in terms of zeros. So NP0 is 4 to make sure the dimension match each other. So here, there's 4 zeros acting as an ancilla. This QR is the quantum register. Number 3 means that we need 3 qubits for it. And the CR is classical register. It used to store the measured results. And then we build the quantum circuit out of the QR quantum register and the classical register. Next, we initialize our state with the initial state we choose, as denoted here. Next, we build our custom quantum operator or custom big quantum gates from the U first, which is the G, which is unitary G operator we just built above. Next, we make it a unitary operations and then apply it to our quantum register. And then we do the quantum measurement at the very end. Put the measuring gate at the very end so we can record the results. Next, let's talk about how to upload your quantum jobs to the QASM simulator, which is a classical simulator, and also to the real quantum machine offered by the IBM Cloud. So first, this count and execute command is basically execute the quantum circuit you built. And then this result command will allows you to get the results, the measurement results from this operation. This QASM simulator is a simulator. And after all your simulations finish, you basically record the results here. Notice this 1.5 is an NC, normalization factors, that used to build the contraction. You may refer more detail into our tutorial file about dilations. But anyway, in the end, we just stack the probability and save the result for our record. When you apply the job to the real IBM machine, because everyone can use it, so there's usually a rather long queue line. So here's a handy trick to help you to maybe save you some of time waiting in the line. That is to find the least busy backend from the IBM cloud. Run this command, and it will return you the IBM backend or the IBM machines that has the least job on it, and it will automatically turn your backend into that. And basically, you just change the backend command here to be the back command here. So now run the same command, and your job will be submitted to the IBM cloud. And you can repeat everything later. It's basically the same in terms of recording the measurement results. Next is a very handy command for circuit visualization. Once you get your quantum circuit, which is a QC here, you can use the transpile command to show you the explicit quantum circuit in terms of the quantum gate you choose. Here, the gate we choose is a CX control X gate, the U3 gate, and the control X gate. You have the freedom to choose whatever basis gate you have here. And then basically, once we transpile the circuit, we use the draw command to give us a very fancy circuit, which is easy to look at. Next, some very handy tools to use is error mitigation. I have to mention that this error mitigation scheme is used it's a rather old scheme, because currently the way to do error mitigations have been improved a lot, and it's been changing all the time. So you're welcome to refer to the IBM menu to search for some very latest way to do error mitigation or error suppression. They have some very recent ways, such as dynamical coupling and zero noise extrapolation stuff. You may refer to the IBM website for that. But here, what does this error mitigation do? This error mitigation is basically, first, it has some built-in or preset calibrators, which is some very simple quantum circuits. And then it will run the circuits on the real machines, because we know what the circuit are. And so after the measurement, we'll know the error, which is the difference between the measured result to the target results. And then we record it and basically undo this error to our measurement results. So in a short sense, you want to run this command before you submit a job to the IBM real machine, and be sure to submit this error mitigation filter to the machine you want to use. And after you run this result, all the information will be recorded in this measurement filter. And then basically you submit your simulation of the open system. And after your simulation, you use the measures filter.apply to your results to apply the error mitigation. Although this error mitigation is not very ideal, it may not improve the simulation result, but still it's a very handy tool to use. And that marks the end of our tutorial. And thank you very much for your listening.